Welcome back, everyone. Today we're going to talk about quantifiers. And quantifiers are going to turn out to be important to put together with the two things we've talked about before to make interesting mathematical statements. Now, there's two types of quantifier. We'll talk about both of them. The first is what's called the universal quantifier. The universal quantifier allows us to make statements about every element of a set. So here's an example. This is the Pythagorean theorem. You've probably seen this before. This is not a statement about a particular triangle T. This is a statement about all right triangles T. Usually our most interesting theorems are going to take this form. They're going to say something about every particular type of thing having some sort of property. There are an awful lot of ways to frame this universal quantifier. Here, that universal quantifier is almost implicit in that I didn't specify what T was. So often this quantifier is hidden in an if-then statement. So really, this statement here, if T is a right triangle, we read as T being an arbitrary right triangle, and we read it that way because we have not previously seen anything that defines T to be a specific right triangle. If someone wants to call this out super explicitly, they will use phrases like for every, or for all. So let me give you a few examples of statements that involve a universal quantifier. This is the statement that for every integer, little z, in big Z, z plus 1 is also in big Z. In other words, what this is saying is that every single integer has the property that if you add 1 to it, you get another integer. Here's another variation. For all x in the reals, x squared is greater than or equal to 0. This is a fact that you end up using all the time in calculus examples of various sorts. Here's another true statement. For every prime p in the positive integers, either p is 2 or p is odd. So this is a universal quantifier. What it's really doing here is letting me give a bunch of different statements all at once. So when I say, for example, for every z in z, z plus 1 is in z, I'm saying 0 plus 1's in z, 1 plus 1's in z, 2 plus 1's in z, 3 plus 1's in z, and so on. So I'm really condensing an infinite list of statements about particular little z's into one statement that encapsulates all of those together. So here's the mean value theorem from calculus. You'll notice this starts with the universal quantifier, namely it's talking about every function that's differentiable on this interval AB. But then it has a new piece, namely it has this there exists, and this there exists is what we call an existential quantifier. So here, when we use this there exists in the second clause here, we're not making a statement about every C in the interval AB. We're making a statement about at least one C in the interval AB, having some property. So let's just do an example of applying the mean value theorem, just so we can make sure we understand what this is saying. So let's take the function x cubed minus x. That's certainly differentiable on the interval minus 1 to 2. It's a polynomial, so it's differentiable everywhere. And so what we're claiming here is that there exists some c in this interval, such that f prime of c is equal to whatever this works out to be. So let's check this. So f of 2 will be 8 minus 2, so that's 6. F of minus 1 will be minus 1 minus minus 1, so that's 0. Divided by 2 minus minus 1, that's 3. So the claim of the mean value theorem is somewhere in this set, there is a C with this property. Let's find it. to go ahead and find this, I'm going to write down the derivative, and then I'm going to go ahead and solve the equation 3x squared minus 1 equals 2. In fact, when I go ahead and solve this, it'll turn into 3x squared equals 3, so it'll turn into x squared equals 1. So I will get x is minus 1 and x is plus 1. Note, both of these are valid choices of c that live inside our interval. Both c equals minus 1 and c equals 1 satisfy this conclusion. And so here's a really important point. All that there exists means is that there's at least one. It could well be that there's exactly one, but it could equally well be that there are two, as there are in this case. Or it could be there are 20, or infinitely many. Maybe every element of the set has the property. All of these are possible. All that the existential quantifier tells you is that there is at least one of these things. At least one element. In this case, it happens there are two. Here are two statements with existential quantifiers. You'll notice the structure of a there exists statement always has sort of two pieces. There's a there exists at the front, and then we describe the set, and then it's followed by such that. So there exists a real number with this property, or there exists a real number with this property. Now, in this instance, as it would happen, one of these statements is true, and one of these statements is false. I'd like you to go ahead and take a second, pause the video, and think about which of these is the true one, which of these is the false one, and why. I'm going to go about doing this by writing down what I know the solution of this equation is using the quadratic formula. Now, this isn't going to work out to be anything particularly nice, but rather notably, my answer has a square root of a negative number in it. And so, in fact, these solutions, they're in the complex numbers. So indeed, this equation has a solution in the complex numbers, but it is not in the real numbers, because the real numbers do not allow me to take a square root of negative 6. If you were taught something about using a discriminant in order to decide whether quadratics have roots or not, then you would just say, okay, b squared minus 4ac is negative, so 0 roots. On the other hand, if I try the same thing up here, then I find that x equals 1 plus or minus the square root of 8 are both solutions to this equation, and those things both happen to live in the real numbers. Having exhibited just one solution, I know that this existential statement is true. So just to emphasize, this one is true, and this one is false. So most math comes down to saying one of these two things. Either everything in a set has a property, or there's something in a set that has this property. And those are the two quantifiers. There's no third quantifier or anything. There's just the for every quantifier and the there exists quantifier. Now, it should be emphasized that quite often in practice, these quantifiers get stacked together. Now, we already saw one example of that with the mean value theorem before, where this is a for every statement, and inside the for every statement was a there exists statement. But I'm going to do a bunch more examples of this so we get comfortable with how these things work when you stack them together. So let's first look at this statement. For every x in the real numbers, there exists a y in the real numbers such that x times y equals 1. I'm not going to think yet about whether it's true or not. I just want to think about what it means. And so, what does this for every x in R mean? It really means that no matter what x you choose, if you write down the appropriate statement here. So again, what's going on with the for every quantifier is that the for every quantifier is letting me make a whole bunch of statements at once. And so it's making this particular statement for every real number. And so if that real number is 1, it's making the statement that there exists a y in the reals such that 1 times y is 1. Definitely true. Y could be 1. If x was pi, it would be saying there exists a y in the real such that pi times y is 1. Also true. Y could be 1 over pi. If x is minus 7, it's saying there exists a y in the real such that minus 7 times y is 1. Also true. Y is minus a seventh. And so I'm claiming this to be true for every real number. Now, if you've been following along, you're either convinced by my 3 examples that, oh, of course, this is just always going to work. Or you have identified that this is not going to work because of one very particular example, namely what this says about x equals 0. For x equals 0, this statement, once I plug in 0 for x, ends up being there exists y in R such that 0 times y equals 1. But whoops, 0 times y is 0, no matter what y is. So this particular line ends up being false. And so even though all of these were true, and indeed literally every other statement for every other real number other than 0 that you write down, those would all be true, but because of this one line being false, the whole statement is false. We can actually fix up the previous example by replacing what had previously been the real numbers with the positive real numbers. In particular, we've now kicked out 0. So, in fact, it is true that for every positive real number, there's a positive real number that when you multiply them together, you get 1. So this statement, this is actually true. So you're going to see a lot of these for every there exists kind of statements. That's the most common way that these two things get stacked together. And what it always really ends up meaning is that you're getting a whole bunch of there exist statements, and you have to decide if you believe all of those there exist statements are true, or if you believe somewhere in there there's a false one. Let's talk about the other direction. What if you have a there exists for every statement? So in this case, we have the statement, there exists a y in R+, such that for every x in R+, we have x times y equals 1. Now, what would this mean? That would mean somewhere in my list of y's in R+, there's a particular y that makes this statement true. So, for example, maybe that y is y equals 2. So, for example, when y is 2, this blue underlined piece would become the statement, for every x in R+, we have x times 2 equals 1. Note, this is definitely not true. And it's not true because of this universal quantifier out front here. Because although it is true that for x equals a half, this statement works out, for x equals 17, this statement works out terribly. And so as a result, this statement for y equals 2 doesn't work. Well, maybe this statement happens to work for y equals 7. If I took y equals 7, I would get the statement, for every x in R+, we have x times 7 equals 1. And this is just as transparently false as my previous attempt. I think at this point you're likely to be quite pessimistic, but you might think, oh, y equals 1 is kind of the obvious one to try. Maybe that works out. But this would say, for every x in R+, we have x times 1 equals 1. Not so much, right? This is basically saying all positive real numbers are 1. Definitely not true. And so our conclusion here is that this statement that we started with, this is false. What's really happening here is that for every x, there's a matching y. And so this statement ends up being true because it's saying, okay, choose the x, then you can find a y that makes this work. However, this statement now is false because there is no single y that works for every x. And the fact that no single y works for every x makes this statement false. Let me give you another version of this, and I want you to think quickly in your head if it's true or false. Again, pause the video, take a moment to dissect this statement, and decide if you think it's true or false. So really, I'm asking here, does there exist a single y that makes this statement true. For every x in R, we have x times y equals 0. You might try y equals 2, just as we started out with before, in which case it would end up saying, for every x in R, we have x times 2 equals 0. Well, that's definitely not true. But if you think about this for a bit, you realize, okay, well, y equals 2 doesn't work. But actually, there is a number I can put here that will make this statement true. Namely, the number y equals 0. And so even though this version was false, the fact that this one is true makes the whole original statement true. So, summary, what's the really important thing to take away from this? Quantifiers don't commute. Sometimes switching the for every and the there exists quantifier will specifically result in changing something from true to false or false to true. So be very careful, and this is one of the things you'll have to practice the most, that you're always reading the quantifiers when they're stacked like this correctly. Let me do one more example of this. And so I want to give you a second to think about this for yourself. Is this statement true or false? So again, to disentangle this, I want to write out what this is doing in a few particular cases. When, for example, x is 2, this is giving me this statement, there exists a positive integer y such that 2 plus y is positive. That's definitely true. For example, y equals 8 would give me 2 plus 8, which is 10, which is positive. Or probably most of you would think, oh, if y was 1, then 2 plus 1, that would be 3, that would be positive. That works just as well. Okay, this statement's definitely true. So what if x was, say, minus pi? That's a real number. Is this statement true? Well, yes, this statement is true. How do I show you this statement is true? Well, one of the easiest ways to show you this statement is true is to just give you an example. So, for example, y equals 4 is an example of a statement that makes this true. In fact, I think you can convince yourself that no matter what x I put here, it's always going to be possible to uncover a y in the positive integers that makes this true. And certainly next week, we'll be able to write down a proof of that. But in fact, in this case, this original statement is true. So, summary, just remember every quantifier is letting you write down a whole bunch of statements at once. And so when even we say something like there exists y in the positive integers such that minus pi plus y is greater than 0, we're really making here a whole bunch of statements. 1 for y equals 1, minus pi plus 1 is greater than 0. 1 for y equals 2, 1 for y equals 3, 1 for y equals 4, and so on. The existential quantifier is just saying at least one in this giant list of statements is true. So the fact that this one's false, this one's false, this one's false, none of that stops this existential statement from being true because that one works out to be true. Whereas the universal quantifier is saying not just one, but in fact every single thing in the list is true. Again, if you're trying to make out what on earth is happening in some statement involving quantifiers, it will make your life easier to put in specific values for the quantifiers just to get a handle on what it is that's being said. Okay, so theoretically this is an intro to proof course among many other things. So let's start with our first thing that we really know how to prove, and we've already kind of touched on it, which is that we really know how to prove statements with existential quantifiers. So just as an example, just to make sure we understand what's going on, let's prove the statement, there exists a prime p greater than 15 such that 2p plus 1 is also prime. What does a proof of this statement look like? A proof of this statement looks like an example. Namely, I'm just saying out of the set of all the primes bigger than 15, one of them at least has this property. So how do I write down a proof of this? Well, I need to just sort of start looking. So let's see, p is 17, then 2p plus 1 would be 35. Well, that's no good. If p is 19, 2p plus 1 will be 39. That's no good. If p is 23, that's the next prime after 19, then 2p plus 1 is 47. And hey, that is prime. And so if I were to write a proof here, it would look much like this. Okay, and this will be our first proof box of the course. This is a complete proof of this statement. So, summary, proving a statement with an existential quantifier almost always amounts to giving an example. And I should say it here, just to be explicit, I really mean here a specific example. One specific example is enough to prove a statement about an existential quantifier. So in this case, writing p equals 23, that was plenty. Now, just in case you're curious, I say almost always because every once in a while, and we'll touch on this a bit in 2 weeks, I think, every once in a while you're able to prove an existential statement without actually producing the example. You can, in some abstract way, show that the example exists. This is usually a very fancy technique. It's not something we're going to see a lot of, but I'll give you at least a little taste of it when we're talking about more esoteric proof methods in a couple weeks. Now, I should explicitly say, I've explained how to prove a statement with an existential quantifier. I have not explained how to prove a statement with a universal quantifier. That will have to wait for next week. But for now, there is one more thing we have to do, and that is to talk about how to negate statements with quantifiers. So let's start with the negation of for every. Remember that a for every statement is really just referring to a whole list of versions of this statement that I've just compressed as ... one for each possible value of x. And the for every statement is the assertion that every single one of those is true. And so the question is, what is the logical opposite of every single one of these things is true? And there's a strong temptation, again because of the fact that opposite has all of these different meanings, to think that the negation is going to be that every single one of these things is false. But that's not the logical opposite of every single one of these things being true. The opposite is at least one of them is false. And that at least one should sound familiar, because that at least one, that's the existential quantifier. So the negation of for every x in S something is in fact there exists an S in S such that, and then not the something. So when you negate a for every statement, it turns into a there exists statement. Let's also talk through what happens when you negate a there exists statement. So here, when I make the statement that there exists an x in S, such that ... again, I'm talking about a statement for every element of S, and I'm just saying at least one of them is true. And what's the opposite of at least one of them is true? It is every single one of them is false. So just like for everys under negation turn into there exists under negation turn into for everys. I'm going to do a bunch of examples of this, I promise. But before I dive into that, I want to note one consequence of this. We said before, proving existential statements are true is simple. Simple might not mean easy. You have to come up with an example. That example might be very rare. It might be hard to find. But ultimately, the proof is almost always going to be, hey, here's an example. On the other hand, we've noted that we're going to have to postpone proving statements with universal quantifiers in them, because that's going to be a bit more nuanced. Now, what I want to point out is both of these things are about when the thing you're proving is true. But proving that a statement is false is the same thing as proving that its negation is true. Because remember, the negation at the end of the day is nothing more than the statement that the statement is false. And so what that means is that when we're proving one of these statements is false, which is easy and which is hard gets exactly flipped. And that's because the negation of a for every statement turns into a friendly there exists statement, and the negation of a friendly there exists statement turns into the less friendly for all statements. So how do we prove existential statements are true? We give an example. How do we prove universal statements are false? Well, we give an example of the negation. And in this case, that is usually just called a counterexample. Okay, so let's as an example, just to show how this works, let's disprove the statement for every prime p, the number 2 to the p minus 1 is also prime. Disproving it means proving that it's false, or if you prefer, proving its negation. Okay, so what is the negation of this statement? The negation of this statement is there exists a prime p such that the number 2 to the p minus 1 is not prime. Okay. That is just following the negation rule that we wrote here. If I negate for every something something, I get there exists a something such that not something something. So, in order to complete this disproof, I'm going to have to find an example to prove this statement, which disproves its negation, which was the original statement. This, however, does not work, because 3 is prime, so it is not prime. 2 cubed minus 1 is 7. The 5th minus 1 is 31. 2 to the 7th minus 1 is 127. We have entered into the realm where it might take you a minute to show that 2 to the 7th minus 1, which is 127, actually is prime. 2 to the 11th minus 1, this is 2047. And in fact, actually, I'll just spoil it for you, this number is 23 times 89. And so this line of work shows me that there's a prime p such that this number is not prime, namely 11, which then disproves this statement. So, when you write down your disproof for a statement like this, your answer should be a sentence like this. The prime p equals 11 is a counterexample, because 2 to the 11th minus 1 is 23 times 89. Now, I do want to point out one of the fundamental weirdnesses of this is that often the length of the proof you write down has nothing to do with how much work it was to find it. Maybe the counterexample doesn't happen until you've checked 1,000 numbers. But still, your disproof will be very short, because it will just be, hey, here's this counterexample. Note, you don't even have to include in your proof. In fact, you should not include in your disproof any of this other work. The only thing that matters, the only thing that's needed to disprove this statement, is one counterexample. And a counterexample is just an example of the negation of a universal statement. That is all counterexample means. It's really just an example. So let's do another example where we practice just negating some of these statements. Again, I'd really encourage you, pause the video, write down a quick negation of each of these. Just make sure you're in good shape to write down these negations, because this is something we're going to be doing a lot. So we know here this for every is going to become a there exists in Z such that. And so the negation of x squared plus 3 equals 7 is x squared plus 3 is not equal to 7. Now, here's a hint. Whenever you write down a statement and its negation, it had better be the case that one of them is true and one of them is false. If you write down a statement and its negation, and they're obviously both true or obviously both false, something has gone horribly wrong. In this case, though, which one is true, the statement or its negation? Well, definitely the answer is the negation. There is definitely an x, for example, 0, such that x squared plus 3 is not 7. Whereas it's definitely not true that every integer has the property that if you square it and add 3, you get 7. It would be rather... I guess it would make math much simpler if that were true, but sadly, it is not. Here, on the other hand, when I go to negate this, there exists x in z such that blah, blah, blah. This is going to become, for every x in z, x squared plus 3 is not equal to 7. Again, one of these should be true and one of them should be false. Which is it? And in this case, it's the first one that's true, because, for example, x equals 2 is an example of an integer such that x squared plus 3 is 7. Note, however, this is all very sensitive, because if I replace these 7s with 8s, now, in fact, it is the second line that is true. There is no integer, which when I square it and add 3, I get 8. And so now, instead of the first line being true as it was when these were both 7, now it is the second line that is true when these two are both 8. But again, no matter what number I put here, as long as these are negations of each other, one of these two will be true and the other will be false. But depending on what number, it could flip-flop back and forth. Okay. Now, how about for all x in z, x is even or x squared plus 1 is odd? Okay, so this for all becomes there exists. And here I have to make sure I have not forgotten everything we've learned about negating statements that have the various other logical joiners, like or in this case. So this becomes such that x is odd, and x squared plus 1 is even. Okay, again, the or became an and. Okay, and I negated each of these pieces. Let's do one more, where in this case, we have a compound statement. That is, we have a for every followed by a there exists. So for every x in the integers, there exists a y in the integers, such that x times y is non-negative. So this for every becomes a there exists. This there exists becomes a for every. And then this x times y is greater than or equal to 0 becomes x times y is strictly less than 0. Note, opposite of greater than or equal to will turn into strictly less. Opposite of greater will turn into less than or equal. So be careful, the equal flips as well. Note a couple things. First of all, remember that there exists phrase carries along this such that. It's like a ne pas in French when you're negating something, if you like. But make sure when you write out your second line, you throw away the such that, because the such that was there to complement that there exists, so we don't want to have that there. Now, often that will make things slightly linguistically awkward. So, for example, if we said for every y in z, x times y is less than 0, sometimes you can just put a comma there. But that can still make things look a little awkward or read a little awkward. So if you want a phrase to sort of pair with for every, in the way that such that pairs with there exists, the phrase we have is just a good standby to put there. It's sort of filler words, really to separate these two equations from each other to make this read a little bit better. Okay, last up for this section, I want to talk about definitions. So I'm going to give us specific definitions that we're going to use for the rest of the class. of a few common terms that we've actually been using so far, but I think it'll be very helpful to have the specific definitions. And it'll turn out that actually, really for these definitions, we're really going to need to make use of all of the stuff we've done with quantifiers and so on. In the last video, when we talked about sets, I defined subsets because it made sense, but I didn't really have a great language for it at the time, because really, the statement about being a subset is a universal quantifier. It's much cleaner to state now, and so if you were to see this definition in a textbook, or you were to apply it in a proof, the definition you really want is this. For sets A and B, we say that A is a subset of B if, for every little a in A, we have that little a is an element of B. The structure of a definition in math almost always has this form. There's this linking word if. Before the linking word is a description of the thing we're defining and what things it might apply to. So here, for example, I've clarified that A and B are sets. It doesn't make sense to talk about being a subset if A and B aren't both sets. So we're talking about two sets, and then we're going to say A is a subset of B. I'm underlining the thing that's being defined. And then following the if, we get the description. For every little a in big A, we have little a is in big B. Again, remember this if is really an if and only if. In a definition, again, by convention, we say if, but this really means if and only if. Now, a thing that's really helpful to do, and that I'll be sure we do through this, is to write down the negation of some of the definitions. So, what does A is not a subset of B mean? Well, it means the negation of this. So it means, in fact, there exists little a and big A such that little a is not in big B. Now, this is a very helpful skill to have, because you might be given, for example, the piece of information that A is not a subset of B, and if you're given the piece of information that A is not a subset of B, that's exactly telling you that there's some element of A that's not in B. Here are official definitions of even and odd. There are maybe equivalent ways you might think of defining these things, but these definitions have advantages when we're going to be using them in proofs, and they're explicitly quantified. So we see that both oddness and evenness are really about existence. Something being odd means there's an integer such that that thing is 2 times that integer plus 1, and something being even means you're just 2 times that integer. Now, I want to note a few things about this. First of all, if you have these definitions, then you can answer 2 things I'm often asked, in fact, 2 things that often get debated on the internet. Namely, is pi even or odd, or is 0 even or odd? Let's start with is pi even or odd. The definition here actually tells us that we're talking about integers when we talk about odd and even. So in fact, the definitions we've written down here do not apply to pi because pi is not an integer. So really, this question is a category error. And by category error, I mean you're asking about adjectives that don't even apply to this thing potentially. So it's neither even nor odd, but it's not just that it's not even and not odd, it's that asking whether pi is even or odd doesn't even make sense. That is what this is saying when I say that this is a category error. On the other hand, is 0 even or odd, or is it neither? Well, now we know that asking if 0 is even exactly reduces to the statement, there exists k and z such that 0 equals 2k. This is certainly true. Namely, take little k equal to 0. This is definitely true, so 0 is even. On the other hand, 0 is a pretty weird number. You might be concerned, maybe 0 is both even and odd. Who knows? So let's check and see if 0 is odd. 0 being odd would be equivalent to the statement that there exists a k in the integers, such that 0 is equal to 2k plus 1. Now, maybe at first blush, it's not super clear what's going on here, but if this was true, then 2k would be equal to minus 1, so k would be equal to minus 1/2. But minus 1/2 has the annoying problem that it's not an integer. So what that means here is that 0 is not odd. And so our conclusion here, 0 is even, 0 is not odd. Tell your friends on the internet. Now, there's a subtle point here, which is that we kind of know, at least aside from 0 and technicalities, we kind of know that every integer is exactly one of odd or even. But it's actually not straightforward to prove that from the definition. I'm going to give you this as a theorem, and so you can use this theorem on the homework. Every integer is odd, exclusive, or even, meaning every integer is exactly one of odd and even. And we'll talk a little bit later about why this is maybe slightly harder to prove than you would think it is. But anyway, the point is, once you have this theorem, then you now know the negation of is odd is that it is even, and the negation of the fact that n is even is n is odd. So you can flip back and forth between these two definitions when you negate them. That is why I'm giving you this theorem. So let's go ahead and officially define prime and composite. I think it makes more sense to define composite first, even though we use the word prime more than we use the word composite. Okay, so pause and think for yourself. A positive integer n is called composite if there exist integers k and l such that what? So probably you at least said such that n equals k times l. However, please note, if you used this as your definition, you would have just defined composite so that every positive integer is composite. Why? Because I didn't make any specifications about what k and l are. So k could be 1, l could be n, and then every number would be composite. So really, I actually want such that n is k times l, and k is at least as big as 2, and l is at least as big as 2. And now this gives us our real definition of composite. So now we can define primes, but it's actually nice that we can now just say something's prime if it's not composite. Now, we have this annoying condition that mathematicians somewhat frustratingly insist that one shouldn't be a prime. But note I hid that in my description of what numbers are candidates to be called prime. So, namely, the way I have written this definition, I am implying that it doesn't really make sense to ask if one is prime or not. Now, I personally believe that, but you could write this in a variety of ways if you didn't like that. Another thing that I've specifically avoided in these definitions is discussing negative numbers at all. So, a lot of times people might ask, is -7 prime? And the answer actually to that is, it depends on your definition. Because in fact, there are very reasonable definitions by which -7 is prime. There are even reasonable definitions by which -1 is prime. But there's a whole lot of mess that ends up being complicated and goes down holes that we don't really want to go down. So I am just omitting any discussion of negative integers in the is it prime or not discussion. Likewise, 0 is omitted here. But one moral I really want you to take away from this is that definitions are cheap. By which I mean, you could define anything to be anything you want. It doesn't get you anywhere to have a definition. The hard work is, once you have a definition, proving things about it. Likewise, I want to emphasize that definitions are flexible, because you'll find out that actually different mathematicians in different contexts will define different words in different ways. Like I just admitted, sometimes people will say -7 is prime, sometimes they won't. It's not necessary for math to work that everyone agrees what every word means. In fact, it can be quite beneficial to be able to slightly alter the definition of the term you want based on the context in which you are working. But this can become quite infuriating, especially to students who are learning things, because there's this whole idea that the things you're learning are supposed to be fundamental truths. And in a sense, definitions can never be fundamental truths. A definition is just a shorter way to say a longer thing. The definition can't contain any truths about the universe. Those have to be saved for propositions and theorems and so on. Let's write down a couple more of these. So our defining is a multiple of. So for example, is a multiple of 3 would be numbers like 3, 6, 9, 12, etc. Is a multiple of 6 would again be numbers like 6, 12, 18, 24, and so on. And so, in fact, to say an integer n is a multiple of an integer m, what that really means is something a lot like our definition of even, which is to say if there exists a little k in Z such that n equals m times k. I want to go ahead and make an immediate follow-up definition, which is I just want to name the other direction. Which is to say, if n is a multiple of m, we say that m is a divisor of n. So, just to give you a couple examples, 12 is a multiple of 4. What does that mean? Well, by our definition, it means that there exists k such that 4k equals 12. And that's certainly true. K is 3. Since 12 is a multiple of 4, we'll say 4 is a divisor of 12, or also 4 divides 12. Okay, so these are different ways of saying the same thing. And just whichever happens to sound most natural, the way you're writing, that's the one you'll end up using. So you'll notice here I did not exclude negatives or 0. So I'm allowed to ask, for example, is 0 a multiple of 7? And so again, I want to make sure we understand we don't get to choose the answer to this once we've written down the definition. This definition knows the answer to this question. We just have to read and apply the definition, and that should tell us the answer. Again, I really encourage you, take a moment, think about this, and then I'll go over it. Okay, so by the definition, what does 0 as a multiple of 7 mean? It means there exists a k in Z such that 0 equals 7 times k. Why does it mean that? It means that because that's exactly what we said it means. I just copied this piece, and I substituted in the fact that I was talking about n being 0 and m being 7. And so that gave me this. So is it true that there exists a k in Z such that 0 equals 7 times k? Of course it is. I can take k to be 0. One last definition for today. Namely, we say a real number is rational if there exists an integer and a positive integer such that x is p over q. Note I restricted q to be positive so that I didn't have to worry about dividing by 0. Now what this usually means is that showing something is rational is usually not that bad because being rational is an existent state. what does it mean if we say x is not rational or irrational? So in other words, I'm asking you, this is our definition of rational, which is there exist these. What is the negation of this underlined part? So my there exists turns into a for every. So for every p and z and q and z plus, we have x is not those. So namely saying something is irrational is really making a statement about every pair of integers. It's saying for every pair of integers, it's not the ratio of those two integers. I do want to address, because I'm sure some of you are wondering, why did this and not become an or? If I look at the original statement, that's an and. And when I negate ands, they turn into ors. Why is that not an or? Is it a mistake? And the answer is no, it's not a mistake. The reason is because, again, logical ands become ors. This is not a logical and. This is an and that is just there linking this p's and z with this q's and z plus. Really, this is an and like in a list. I would like apples, bananas, and oranges at the store. That and is not a logical and. Neither is this one, so it does not get flipped. Notice you would have a bit of a giveaway if you accidentally did flip this to an or, because the statement you got at the end wouldn't make any sense. Because it would be for every p in z or q in z plus, we have this thing, but the or doesn't actually work. I can only take p over q if I know where p is and know where q is. So again, there's a lot of subtleties here. But, as a last note of today, and of this week, I want to note, this is why showing numbers are irrational is really hard. So when square root of 2 was shown to be irrational, it was such a big debacle that it led to a lot of murders by the Pythagoreans, who did not like the idea that this number was irrational. It was very upsetting to them. But numbers like pi and e, that you probably know are irrational, were not known to be irrational until the 1700s. So these proofs are actually quite complicated, and ultimately the reason why they're complicated is that somehow you have to show this for every pair of integers you don't get pi when you divide them. That's not a super easy thing to show. Alright, I'm going to wrap up week 1 videos here. Now I'll see you in week 2 when we'll be talking about proving things. But for now, have a wonderful weekend, and I'll look forward to meeting you all in Zoom.